It is just past 12:30 on a mild January afternoon in 1919. People working along Commercial Street in Boston's North End hear a low, structural growl. Then comes a series of sharp, overlapping cracks, like the rattle of a machine gun, as 2.3 million gallons of molasses violently breaks free. The initial wave rose 25 feet high and tore through the crowded neighborhood at over 30 miles an hour. The immense kinetic force of the heavy liquid swept people off their feet, crushed wagons, and shattered buildings. A fresh shipment of molasses had arrived from the Caribbean only 2 days earlier. Because it was fresh, that load was still warm, roughly 5 degrees Celsius warmer than the January air. That extra heat lowered its viscosity, allowing the dense syrup to flow at a terrifying speed. As the liquid spread out across the waterfront, the 40-degree winter air rapidly pulled that heat away. Fluid dynamicists who later studied the collapse found that cooling molasses from 10 degrees Celsius down to 0 roughly triples its viscosity. The cold air turned the spreading flood into a setting, cement-like trap. Rescuers waded in and found themselves stuck as the thickening syrup gripped everything caught in it. The physics of that January afternoon claimed 21 victims. Almost immediately, the tank's owners, United States Industrial Alcohol, reached for a defense. Their lawyers claimed anarchists had destroyed the vessel with a bomb. In 1919, a year defined by political violence, a sabotage claim was highly plausible. It triggered a massive, multi-year legal inquiry involving thousands of witnesses, one of the longest and most expensive in Massachusetts history to that point. Proving the actual cause of the failure requires structural math and forensic engineering. When you examine the chemistry of the steel, the evidence suggests the true source of the destruction was the container itself. To understand the mechanical failure, we have to look at the project manager. The company wanted a massive holding tank constructed quickly on the waterfront. The man they put in charge of building it was a corporate treasurer named Arthur Gell, who had no engineering or structural training. Gell chose to skip the standard hydrostatic test, which would have involved filling the tank with cheap, harmless water first to prove its integrity. Instead, the company immediately pumped it full of valuable molasses. Molasses weighs nearly 12 pounds per gallon. Inside a structure standing 50 feet tall and 90 feet across, the fluid pressing outward on the bottom rings generated tens of millions of pounds of force. This cross-section compares the tank walls to the required safety thickness. The half-inch plates were 50% too thin. An internal gauge shows baseline stress on those bottom plates exceeded 31,000 pounds per square inch, leaving almost no safety margin. The tank was mathematically compromised the minute Arthur Gell signed off on the blueprint. It was unsafe from the moment it was filled. Thin walls alone were only half the failure. The steel was hiding a second flaw. The metal plates were severely starved of manganese, an element essential for keeping steel tough in cold environments. This graph illustrates the ductile to brittle transition temperature. Above this threshold, steel is ductile and will stretch before failing. Below it, the metal becomes brittle and snaps instantly. Because of the missing manganese, the tank's transition threshold was 59 degrees Fahrenheit. On the day of the collapse, the Boston air was 40 degrees. Sitting 19 degrees inside its brittle range, the steel could only shatter. Finite-element analysis pinpoints where the fracture started. A manhole cut into the base created a stress concentrator. A single rivet hole directly above it carried nearly 18,000 pounds of stress, double its intended load. The heavy load overwhelmed the steel between the fasteners. The vertically aligned rivet holes acted like a perforated dotted line, allowing cracks to unzip through cold, brittle plates at 3,000 feet per second. The explosion witnesses described that afternoon was the violent kinetic release of an overpressured, brittle vessel unzipping from a single point of failure. Back in the courtroom, the company's bomb theory collapsed. A court-appointed auditor listened to a parade of metallurgical and structural experts who used steel chemistry and safety factors to prove the tank was structurally insufficient. The most damning evidence presented at the trial did not require a microscope to understand. It was the visible leaks. Residents testified that the massive structure had groaned under pressure. Molasses had visibly run down the sides of the tank for 3 full years. The company's response was to order a fresh coat of brown paint for the exterior, ensuring the seeping molasses would blend in. That coat of paint transformed a sequence of engineering errors into an active, deliberate cover-up of a blaring structural alarm. The auditor's ruling forced the company to pay hundreds of thousands of dollars in settlements. This decision established a legal precedent. Companies were responsible for the technical soundness of their infrastructure, regardless of their internal staffing choices. The public fallout from such an expensive, high-profile failure made the previous lax oversight of industrial construction untenable. Forcing finance-led companies to bear the full cost of engineering negligence created a sudden, massive demand for accountability. This disaster became a primary catalyst for state laws requiring professional engineering certification. Responsibility shifted from treasurers like Arthur Gell to licensed experts who are legally required to mathematically verify, sign, and seal their plans. The rigorous building codes and certified structural margins we rely on today are the direct result of the lessons learned from 1919. They ensure that when a structure begins to fail, the warning can no longer be silenced with a coat of paint.